Okay, so let's dive into a really fundamental concept that helps us build AI we can actually trust. It's all about answering a question that gets right to the very heart of what machine learning is. Right, this one. Is the model actually smart, or is it just a good test taker? This is the core problem of what we call generalization, and it's what separates a useful model from a totally useless one.
So let's start by framing the challenge. It's a classic problem, one that every single person who works in machine learning runs into. It's called overfitting. Think of it like this. Imagine a student who just memorizes every single answer in the textbook. They get a perfect score on the homework, but the second you give them a new problem they've never seen before, they completely fall apart because they never actually understood the concepts. That, right there, is overfitting in the world of AI.
So, to fight this, machine learning has a pretty core strategy for learning from data. See, the goal isn't just to be right on the practice questions, it's to learn how to be right in general.
Now, I know this diagram looks a little intimidating, but it boils down to this beautifully simple idea called empirical risk minimization. Honestly, the strategy is super straightforward. We just want to find a model that makes the fewest possible mistakes on the training data we show it. That's it.
But here's the catch. A really crucial point here is something called the hypothesis class. Just think of it as the set of tools our AI is allowed to use to solve the problem. It kind of defines the boundaries of what the model can even try to learn. And, the choice of that toolbox is absolutely critical. If it's too simple, like just giving it a screwdriver, it might not be powerful enough for the job. But if you give it this giant, overly complex machine, it can build something so perfectly specific to the training data that it's useless for anything else. And that's exactly where that overfitting problem sneaks back in.
So this brings us to the million-dollar question, right? If we want to avoid building these over-specialized models, we need some kind of formal mathematical way to measure the complexity, the raw power of our model's toolbox.
And that brings us to the heart of this explainer. It's a really beautiful concept from statistical learning theory called the Vapnik-Chervonenkis dimension. Yeah, I know, it's a mouthful. So we just call it the VC dimension. And this is basically our ruler for measuring a model's complexity. Now, before we can define the VC dimension itself, we have to get our heads around this other key idea, and it has a kind of dramatic name, shattering. We say a model's toolbox can shatter a set of points if it's so flexible that it can create any possible grouping of them you could possibly imagine. Okay, check this out, because this slide shows it perfectly in action. Look at that H1 column. When you give it 2 points, there's that one black and white labeling that it just can't make, and it's marked with that red X. So it fails to shatter 2 points. But look at the more complex model, H2. It can handle all the combinations for 2 points, no problem.
So with that idea of shattering in our back pocket, the definition for VC dimension is actually super simple. It's just the size of the largest set of points that your model's toolbox can successfully shatter. It's one single number that captures the model's capacity. And this is where it gets really cool. Check this out. In 2D, it doesn't matter how you arrange 3 points on a flat plane, and it doesn't matter which of the 8 possible ways you want to color them black or white, there is always a straight line you can draw to separate them correctly. But, and this is a huge but, that power has a limit. Try as you might, you can always find a way to arrange 4 points and a specific labeling, kind of like a checkerboard pattern, that is literally impossible for one single straight line to classify correctly. It just can't be done. And that is the big takeaway here. For the set of all possible 2D linear classifiers, basically all straight lines on a plane, the VC dimension is exactly 3. It can shatter any 3 points, but it can't shatter 4. We've got our number. Okay, great. So we have this number, this measure of complexity, it's 3. But so what? Who cares? Why is having a finite, measurable number for our model's power so incredibly important? What does it actually let us do? Well, it turns out it's the key that unlocks what's called the fundamental theorem of pack learning. It creates this amazing chain of logic. It basically says, if your model's VC dimension is a finite number, then it is probably approximately correctly learnable. And that's just a fancy way of saying our simple strategy of minimizing mistakes on the training data is actually going to work out in the real world.
What this theory gives us is a powerful mathematical guarantee. It's often written as a really scary-looking formula, but honestly, you can just forget the formula and remember this one simple phrase. Your error on new, unseen data is going to be less than or equal to the error you got during training, plus some kind of penalty for being too complex.
And that's the punchline. The VC dimension that we just figured out is the engine that drives that complexity penalty. So a model with a higher VC dimension, a more powerful toolbox, well, it pays a bigger price. It has to be way better on the training data just to justify how complex it is.
This is incredible because this insight gives us an actual practical strategy for building better models. It's not just about getting the training mistakes down, it's about finding that perfect balance.
This whole principle is called structural risk minimization, and this graph shows the balancing act perfectly. You've got the training error, that's the black line, and it goes down as the model gets more complex. But you also have the complexity penalty, the blue line, which goes up. Our real goal is to find the lowest point on that red line, which is just the sum of the other two.
So in practice, what this means is we don't just pick one model and hope for the best. We test a whole range of them, from the simplest to the most complex. For each one, we find its best possible performance. And then we use that guarantee to add the complexity penalty. The winner is simply the one with the best total score.
So you see, the VC dimension isn't just some abstract ivory tower theory. It's the foundation that lets us build guardrails around our models. It gives us a real, principled way to control complexity, and that gives us the confidence that our AI is actually learning, not just memorizing.
And this leaves us with a final thought to chew on. Today's AI models, things like large language models, they have toolboxes that are almost unimaginably huge. The challenge of measuring, of understanding, and of controlling their true power, well, it's more critical and frankly more fascinating than it has ever been before.